A coffee before we start, please do that. Water, tea, cookie, it's all over here, thanks to the Kluane Lake Research Station. A big round of applause for Kim and the team. She's right there. Again, thank you for being here. For those of you who are lucky enough not to know me, my name is Michael Schmidt. About a month ago, I got a phone call from the Yukon Science Institute saying, hey, you're not doing anything. Would you like to organize a talk for us? So here we are. And I'm happy to have an old friend and colleague make the trip from Victoria up here. Before we go any further, a few housekeeping things. Emergency exits through that door to the left, up the stage and out the back door. You all know this. Through that door and then out in the same way you came in. That's about it for that. We're going to talk or somebody's going to talk for about 45 minutes or so. We are recording the presentation so that it will be made available after the fact for people who can't be here tonight, or if you want to hear it again. We will, at the end of the talk, have questions, and because we're recording, we're asking you to wait for me to come around with the microphone. Please use the microphone. Please make the questions short and sweet. We don't need lifetime stories, just quick, smart questions. That would be great. And after that, we have a little demo here to show you what earthquake waves look like when you jump up and down on the floor. So thank you to the Yukon Science Institute, Yukon U, Village of Haines Junction, Kluane Lake Research Station, and the volunteers who helped us tonight. Start with Nick up top on audio and lights and generally keeping things rolling for us. Marguerite, Elsaby, and of course Kim. It's a huge pleasure to have Andrew Schaeffer make the long trip from Sydney, British Columbia, to Haines Junction, Dakwakatum, here on the traditional territory of the Champagne and Aishihik First Nations. Andrew is a research seismologist with the Geological Survey of Canada. He is based at the Pacific Geoscience Centre in Sydney, BC. I left that establishment just before he came. I had fair warning that he was coming, so I got the heck out of Dodge. Seriously though, we encountered each other some years before that when he was doing his postdoc back in Ottawa. His research focuses on the tectonics of Western and Northern Canada. He completed his BSc and MSc at the University of British Columbia, his PhD at Dublin Institute for Advanced Studies and University College Dublin in Ireland, and his postdoc at the University of Ottawa. He splits his time between developing and applying modern analysis techniques, and also spends a lot of time getting into the field. We used to say at the PGC and the GSC, you can't separate a scientist from their tools. And he speaks to this, and it's totally important. A lot of scientists don't. Andrew does. Please welcome him.
Yeah, thank you very much, Mike. Very nice introduction. And yeah, I have not been this way for a while, but back in 2004 to 2007 as an undergrad student, I spent a number of very enjoyable summers working out of KLRS. But this is my first time being back this direction in the Yukon since 2007. Much of my recent work has been more up the Dempster Highway and on the Yukon North Slope and southwestern Northwest Territories. But today, so we're all here, I assume many people in the room probably felt some shaking on, okay. I think, can you click on the slideshow? Maybe we're just on someone else. Yeah, there we go. Okay, thank you. So show of hands, who did feel the earthquake? Yeah. In Whitehorse, it was a little bit more 50-50, far enough away. So the vital stats for that earthquake, it was a magnitude 7. This is the largest onshore earthquake within Canada in the last 75 years. So previously, the largest onshore earthquake in Canada was the magnitude 7.3 beneath Vancouver Island in 1946, beneath Courtney. There have been other large earthquakes, the Haida Gwaii earthquake in 2012, but these are just offshore. So this was the largest onshore in quite some time. It occurred beneath Mount King George and the Hubbard Glacier in the St. Elias Mountains, of course, Kluane National Park, within the traditional territories of the Kluane and White River First Nations. And as you all can attest, as many across the Yukon, the shaking from this event was felt widespread across the Yukon. So this map here, we're looking at the star. This is where the main shock of the earthquake occurred, beneath the St. Elias ice fields. And then these squares are the aggregated "Did you feel it" reports that we receive on our webpage, where the size of the squares gets smaller the more people report in that area, so you can get more detail. And the colors, there's no color bar here, but essentially the bluer colors are lower estimated shaking, and the brighter colors, the yellows, are more estimated shaking. And so for those of you that did fill out a survey, there's a number in both Burwash Landing, Destruction Bay, and Haines Junction area that did. The questions that are asked that might seem a little pedantic are actually a fairly standardized set of questions that are used to estimate a shaking intensity for a region. And this is, we'll come to this later on when I talk about local site amplification, but this sort of data is very valuable for us when we're looking at revisiting and rebuilding and updating seismic hazard models, because it gives us an idea about what sort of local amplification may happen. We're quite fortunate that this earthquake, although it was magnitude 7, it was quite remote. So we don't know of any casualties and no structural damage to the built environment. So we're not aware of any structural damage to infrastructure, road corridors, and the built-up environment. This, of course, doesn't include things that may have fallen off shelves and that sort of thing. The epicenter area is uninhabited. We're quite lucky that this didn't happen in the summertime, as there could have been quite a lot of climbing activity in that area. And as you'll see from some photos later on, there was a lot of ice avalanches and rockfall that happened in the vicinity of the earthquake. So just quick outline of what we'll try to cover today. And if I go too long, Mike will give me the hook and pull me down. We'll set the scene, why we have earthquakes here. We'll talk about the Hubbard Glacier sequence itself, the main shock and the aftershocks. Then I'll move to talk about how we study these earthquakes, the equipment we use, some of the other techniques. We'll look at some local studies on site amplification, that is, how earthquake shaking is felt in a local community and how it varies. And then we'll finish with some key takeaways and a little bit of discussion on preparedness. So setting the scene, why does the Yukon have so many earthquakes? And it comes down to largely three main things. There's three ingredients here. We have the Pacific Plate, which lies off to the southwest, and it's moving to the northwest at about the rate that our fingernails grow. Being dragged along or pushed by the Pacific Plate is something called the Yakutat microplate. We'll come to a map with these in just a second. And because the Pacific Plate is moving, it's shoving the Yakutat microplate into Alaska and the Yukon. And finally, we have the North American plate, and this lies on the other side of what we call the North American Cordillera. That is essentially all of the mountains that lie between the coast and the stable, what we call cratonic shield once we get through to Alberta. So BC and the Yukon are predominantly all Cordillera, areas with lots of mountains built and being built. And it's the North American plate that acts as this backstop, which doesn't move, and essentially BC and the Yukon are getting squished in between the Pacific Plate and the North American Plate. So here's a map showing these things. We have the Pacific Plate down here. This is the Yakutat block that I was talking about, and the Pacific Plate is moving with respect to North America up this way, and it's jamming this Yakutat block into the corner of the Yukon and southeastern Alaska, and it is responsible for building the St. Elias Mountains, which are one of the fastest growing mountain ranges in the world, 5 to 10 millimeters per year of uplift in some places. There's a number of major fault systems that cross-cut through BC and the Yukon. This is the Denali Fault, which runs right along the side of Kluane Lake. And then we have the Tintina Fault, which runs right through the middle of the Yukon and Mackenzie Mountains. There's a lot more faults that are on this map, but these are those main huge structures that cut through BC and the Yukon. A cross-section through this region, going from the Pacific Plate here to essentially what we are calling the North American Shield. This is this stable backstop. We start here. We don't need to worry about all the details on this plot. We're just going to look at topography. This is the Yakutat block that's being thrust beneath this corner here. And that is causing essentially the St. Elias Mountains to be crunched up and thickened and built. That's the rapid growth of the St. Elias Mountains. And there's all sorts of faults that cut through this mountain range to help with that process of building. And it's those faults that were activated during this earthquake. We then have deformation throughout the cross-section in the interior portions, and then major building of the Mackenzie Mountains on the other side. We can do a whole separate discussion on those another time. So this, of course, was not the first big earthquake in the Yukon. There's been many, and there's been quite a few felt earthquakes over the last several hundred years. In more than 100 years. So in 1899, there was a magnitude 8. This is referred to as the Yakutat Bay sequence. In 1958, there was a major earthquake on the Fairweather Fault. It's hard to see the line here, but the Fairweather Fault comes all the way up to the Yukon, and it actually connects to the Queen Charlotte Fault that's down at Haida Gwaii. So it's a very large, major strike-slip fault, thinking of the San Andreas Fault, where the plates are just sliding past each other. This actually triggered the Lituya Bay mega tsunami. Lituya Bay is a glacial fjord, and the shaking from this earthquake caused a major landslide, and it slid into the bay and caused a tsunami that's estimated to be as high as 500 meters in some places. In 1940, we had the Richardson Mountains doublet. This is up not too far from where Eagle Plains is. Those was a magnitude 6.4, 6.5, and a magnitude 6.2 to 6.3 that happened about a month apart. Then 1964, this is the Great Alaska Earthquake that occurred in the region of Anchorage. 1979, there was a magnitude 7.5 St. Elias earthquake. 2002, the Denali Fault, almost magnitude 8 earthquake, which occurred in this region, and this was widespread felt across much of the Yukon. And on maps like this, while we usually plot earthquakes as dots, when you're talking about an earthquake that big, they're not a dot anymore. So the part of the Denali fault that ruptured in that earthquake was actually 340 kilometers long. So it's actually a significant amount of area that is affected by that earthquake. It's not just a dot like what we draw on these maps. And then in 2017, there was the Kelso Lake earthquakes, the magnitude 6.2 and 6.3. This was felt quite strongly in Haines Junction. I imagine a number of people probably felt those. And then, of course, we have the earthquake that was just about 2 months ago, which, again, the largest onshore earthquake in 75 years. So a lot of the earthquakes concentrated in the southwest corner, and a lot of earthquakes distributed through the Mackenzie and Richardson Mountains. And all of this to say, big earthquakes have happened before, and they will happen again. So let's talk a little bit more about this recent earthquake, what actually happened, or what we understand to have happened so far, and what, well, from a scientist and a nerd, what makes it so special. And it's easier to say this when we know that nobody was injured by this earthquake. So what happened? It was a magnitude 7 earthquake. We know that it was a relatively shallow earthquake. It had to have started less than 10 kilometers depth in the Earth's crust, probably between 5 and 8 kilometers. The amount of fault that ruptured was about 50 kilometers in length. Quite a bit shorter than the magnitude 8 Denali, but still 50 kilometers is a sizable amount of space to rupture. And as of January 6th, there was more than 3,500 aftershocks that we've recorded. And I'll show a figure later on. As of the end of February, that's climbed to about 4,500 aftershocks, which with a big earthquake like this, that sort of aftershock sequence is expected. We can take a look at what that looks like. We'll look at this in a map in a moment, but it was actually quite a complicated rupture. It started with strike-slip motion, like what we talked about before, plates sliding past each other sideways. But about halfway through the rupture, beneath the area of Mount King George, it actually transitioned and became partially a thrust earthquake. So that is where the plates are now moving vertically beside each other. And this highlights, we'll see in a second, that actually there's more than one fault involved in this earthquake and the aftershock sequence. And that's what I'm saying here. So it activated a secondary fault that got triggered by this earthquake. And actually the largest aftershock that happened on New Year's Eve or New Year's Day, depending on your time zone, happened on that second fault. And we'll see from some of the photos from the YGS flyover that the strongest shaking was concentrated beneath Mount King George. When they got back on that Friday, and I was talking to one of the geologists that was on that flight, their words, they said, it's unbelievable. Mount King George is just obliterated. So I mean, the mountain is still there, but it got shaken to pieces. And we'll see that in some of the photos. Okay, so this plot, there's a lot on this figure, and we'll go slow. So there's been a significant aftershock sequence associated with this earthquake. As we look along this axis, this is days. So December 6th, when the earthquake happened, up to January 6th. This top panel, this is the magnitude of earthquakes, and each of these dots represents an earthquake that's been detected in that immediate area around the Mount Hubbard Glacier that was part of that earthquake sequence. So this one right here, that's the magnitude 7 earthquake that happened at 1:41 local time, the main shock. And then there's so many earthquakes in this period of time that they actually all plot on top of each other. But you can see over the course of days, the number of earthquakes decays away slowly. This is a relationship called Omori's law that tells you how quickly the amount of aftershocks you have decay is a function of time based on the size of the earthquake. And that's why it's really important in the immediate aftermath of the earthquake for there to be discussion amongst, for example, emergency management organizations, because there will be aftershocks. And of course, I imagine many of you felt some of the aftershocks from this sequence. So the length of time and also the amount of aftershocks is dictated by a lot of things, but mostly by the size of the main shock and how complex the region is. The more faults, the more aftershocks you can have. And interestingly with this, this is the second subsequence or mini sequence associated with the New Year's Eve earthquake, which took us a little bit by surprise. We weren't actually quite expecting to see any more a magnitude 6 pop up. But you can see the same shorter decay associated with this magnitude 6. And throughout this whole time, we've seen quite a number of magnitude 3.5 to 5s fairly consistently throughout this month of data, as these are less likely to have been felt just by how remote the earthquake is, but they continued to happen. These bottom two plots, these are related to the Did You Feel It reports that get submitted. So again, as a function of time, each of the major earthquakes is a color in these plots. So the main shock is this orange. The first significant aftershock is green. This brown one was one of the aftershocks that was felt early on. This was on December 8th. I think that would have been Monday or Sunday. No, Monday, sorry. And then this is the New Year's Eve, New Year's Day one in gray. On this panel, again, same colors. This is the distance away from the earthquake that the reports were submitted up this way, and this is the calculated strength of shaking. So for instance, this band here is reports submitted in Whitehorse. This band is reports submitted in Haines Junction and Burwash Landing. And you can see that the X's here are much bigger. And that matches that the shaking that was felt here is much larger than the shaking that was felt in Whitehorse. And one of the things that really stumped us for a number of days is this peak here. This is reports for the main shock and the December 8th aftershock, but they're being submitted on December 12th. And we actually wondered if the clocks on one of our computers was broken and it was assigning the wrong time to the reports. But after going through this for a while and then discussing with our YGS colleagues, actually, this dashed black line is when the YGS submitted a Facebook post with all their pictures of the earthquake, and they included links to Did You Feel It reports and information. And that is actually what spurred as many people to submit Did You Feel It reports for the main shock and the December 8th earthquake as actually on the day of. So it's just, we all know social media has a way of traveling, but this was another example of where it kind of meets with science. Okay, very similar plot, but on the previous slide, we were looking at the time period right in here. So that first month of data between these orange bars. Now I've expanded this and I'm including earthquakes out to a couple days ago. I think February 28th or something like that is when this cut off. And this is just to show that there are still a lot of earthquakes going on. None of these being felt. This is the prior 2 weeks in that same area, and there's essentially no earthquakes. There's less than 5. There's 3 to 4 very easy ones to see. And this 2 weeks of data is pretty representative of the last 2 decades of modern instrumentation. We didn't really see much in the way of activity in this particular region. And now it's continuing to essentially ring. And this sort of background level of activity could go on for several years. Now that this area has been shaken and disturbed, lots of the smaller faults in this area will continue to pop off. But this is unlikely to result in another big one on this fault. That stress has been released now. And as I was saying here, this can continue like this for some time. There might be the odd 4 or 5. This will slowly tail off. The similar sort of earthquake beneath Haida Gwaii, the disturbance in activity lasted for almost a decade in terms of how long it took to return to background levels. And this is something that is to be expected. So let's talk a little bit about the connector fault, not an amazing name, but it comes from a progression through different faults connecting each other. And this is where this earthquake is just really fascinating from a scientific perspective. So it's a long hypothesized fault. I would say that the scientific community has been divided as to whether they believed it was a confirmed fault or a hypothesized fault. It's very clearly a confirmed fault at this point. Mike would say that it was a confirmed fault already from GNSS data. I would agree, but not everybody in the scientific community would. But now most will be convinced with the aftershocks, main shock and aftershock sequence here. So what is the significance of the connector fault? So we're zoomed in on that previous map. So here we have the St. Elias Mountains. We've got Haines Junction, Burwash Landing, Kluane Lake, and Whitehorse. We have the Yakutat block that I mentioned before being shoved in here. And this star and the green dots are where the main shock and the aftershock occurred. This red area here, going all the way down to through the Alaska Panhandle, connects up with the Queen Charlotte Fault. This is the Fairweather Fault. And up here, we have the Denali Fault in Alaska. And this is the Eastern Denali Fault running through Canada. This is where the 2017 earthquakes were. Based on how this Yakutat microplate is being shoved into here, it's been hypothesized and shown with GPS instrumentation that there must be some major fault that links this piece of the Fairweather Fault with the Denali Fault and this piece called the Tachunda Fault that runs through here. However, we don't have any bedrock mapping in this area, or very little, because this whole area in here is the largest non-polar ice cap, the St. Elias Mountains. And so we simply just don't have that many direct observations to see if there's other obvious visual evidence for faulting, as you would in some other places where you can go to the ground and see the contacts and see the faults. And as you can see from the earthquakes that are on this map, there are some earthquakes in this region, but not that many. I'm excluding all of the earthquakes, out in these areas for clarity, because otherwise all we would see on this map is dots. So we can still see things. So having this earthquake and its sequence, this essentially provides this final piece of conclusive evidence that indeed there is something connecting the Fairweather Fault to the Denali Tachunda. There's a little bit of seismicity in the northern section of the connector fault that we've known about before, but there was nothing down here. So we're now able to connect these areas with seismic results as well, even though we're not able to see the bedrock itself. So this earthquake and its aftershock sequence lit up this hidden fault, this fault that we can't see. So on this map, we have the main shock. This was the magnitude 7. This dot represents where it started, okay? But it ruptured the whole length of this region over its kind of 20 to 30 second long rupture. So it started here and ruptured to the northwest. And then all of the rest of the green dots are those 3,500 aftershocks that have been detected and located in this area. And what they show, at least in the southern half, is they line up quite nicely in a relatively linear fashion that essentially trace for us where that fault is in the subsurface. We're not showing depth here, but actually they line up nicely on a dipping plane, a dipping fault in the subsurface. When we get to Mount King George, right here, you notice that there's actually somewhat fewer aftershocks in that area. And from observations, this is also where YGS have said that it just looked obliterated. Well, this is because this is likely where the maximum amount of slip that happened on the earthquake. So when the plates slide past each other, you don't get the same amount of slip on all parts of the fault. There's usually going to be one part of the fault that slips more than others. And that's often where the most damage can be, and it's often where you end up having the fewest aftershocks. And that's because you've released most of the stress that's stored in that fault in the area where it slipped the most. And that's why there's fewer aftershocks there. There's less stress left to release. The December 31st, January 1st earthquake, that is this one here. So when I was talking before about this being a complex rupture, we can see that there's a feature defined in this orientation, but there's also likely some sort of feature defined like this. And this is what we refer to as a conjugate fault. It's at an almost 90-degree angle to the other fault. And so the main shock likely ruptured along this orientation fault all the way to here, and then quite possibly continued a little bit along this way, but also ruptured a segment of this fault. So it jumped to a new fault, and the reason we suspect that is we don't need to worry about what these funny circles are in any detail. They're called beach balls. What they do is they tell us how the fault moved. Something like this is a strike-slip fault, and something like this is a thrust or reverse earthquake. So side-to-side motion and up and down motion. And this beach ball is the mechanism for the main shock, and it's pretty ugly. It's a weird combination of one of these and one of these. And that's what tells us actually that as this earthquake happened, it started as a strike-slip earthquake. And then as it reached around this area, it became also a thrust-type earthquake. And that's important because there's likely a lot of these sort of conjugate faults all throughout this area. And while you can still have an earthquake rupture both of these faults, because of the complexity of the rupture, the overall magnitude of this combination earthquake is likely a little bit smaller than it would have been if it continued as a single strike-slip earthquake, because it would have ruptured a longer distance. These also can, in times, act as a way to stop or slow down a rupture from continuing. So this is why it's such a complex area, and there's a lot of research that's going to continue to look at this aftershock sequence in more detail to give us a more detailed picture of where the next fault segments might be, how did these ones actually rupture. And all of that feeds back into our seismic hazard models. So from what we know so far about this earthquake, what does this mean going forwards? i.e., is there lingering seismic hazard in this area, and what might it imply on neighboring fault segments? Well, to the south and to the north, there's other segments of these faults that may be ready to host earthquakes. And we know that they're in our hazard models as being seismogenic. So 20 to 30 kilometers south of the rupture is the 1958 magnitude 8. So there's a portion that hasn't ruptured between that 1958 earthquake and this one. And then to the north, there's 225 kilometers between the northern extent of this sequence and the southern extent of where the Denali ruptured. So has this event increased or decreased the stress on those neighboring fault segments? And that's something that's being studied now. It's not something that's super simple to work out. We have to model the main shock and all of its aftershocks and how that transferred stress to see whether those segments of the faults lay in areas that might increase or decrease in their stress. There's also the Eastern Denali Fault, which lies more than 100 kilometers to the northeast along Kluane Lake and going north towards Beaver Creek. It's quite a long way away from this fault and where these earthquakes happened, but the similar sort of analysis will be used to look at whether this earthquake and its sequence might have any impact on the Eastern Denali Fault. It's quite a long ways away, so it's probably not going to, but that is something that is going to be active research for the ongoing months to years to look into that. But the key takeaway is that while this event and sequence likely is going to have some amount of impact on the neighboring fault segments, this whole area is also already in the National Seismic Hazard Models. It's included as a region, as a zone of earthquake activity rather than individual faults. And so research that will go into this area will essentially refine the hazard model to reduce it to areas of specific faults rather than zones. And this will allow the hazard models to be more precise about what sort of shaking should be expected and at what sort of recurrence interval, which then feeds back into the building codes that are used for building our buildings and our infrastructure. Let's look at the landslides, avalanches, and ground failures. So this was from this overflight by the YGS. So just to start, this is from space. So this is an optical satellite view. The first shot is November 28th. The second shot is December 9th. You can see the extent, these white regions. Those are the ice fall and ice avalanches that were produced by this earthquake. This is Mount King George in here with the fault running essentially through here. So we can see from these space observations quite a lot of the runout from the ice and snow, but it doesn't show a lot of the rockfall. This is a summary figure put together by the YGS. They've documented more than 200 landslides and avalanches in the immediate vicinity of Mount King George based on satellite imagery and their overflight. The black areas are the runouts of landslides, and the white areas are runouts of large avalanches. And the blue is where they observed damage to the glaciers. So this would be broken snow bridges or seracs that have fallen. And then this is that main shock sequence that we have and the conjugate fault from the other figure. What they didn't observe was a surface rupture. So we didn't see a big crack running through the middle of the glaciers, which implies that the earthquake perhaps didn't actually break the surface of the Earth's crust, because if it had, it probably would have also broken the glacier itself. Here's a couple pictures of this. So here's Mount King George looking to the north-northwest. This is the source area of the largest landslide that was observed. And then this distance that this landslide traveled is about 7.5 kilometers. And the runout is almost 2 kilometers wide at the end of the fan out onto the Hubbard Glacier. And then this is looking from the other side, from the west-southwest. This is Mount King George. This vertical face is about 1,700 meters from the top of the mountain down to the glacier, where all sorts of these faces were they just fell, were pulverized, and landed on the glacier below. They were just dust by the point they'd reached the bottom. When they were there, they knew that activity was still going on. Rock dust was still floating in the air, and they observed small rock falls on this face of the mountain, and they're pretty sure that this landslide had to happen sometime between December 11th and the hours before they arrived. It was very fresh. A few surprising findings here. They saw fewer landslides than one would expect for this size of earthquake. Empirical relationship would suggest that larger areas get affected by earthquakes this size. Possibly this is because of the midwinter timing, colder temperatures, frozen ground, the slopes are ice cemented. There's also permafrost, so perhaps this permafrost frozen ground may have held the slopes together. This is important because in the future, as permafrost thaws, as we have less ice, it could mean that earthquakes are capable of triggering more landslides. Okay, let's go quickly through how we study earthquakes in remote regions using a few tools. For me as a seismologist, I use seismic instruments. We'll talk briefly about geodetic instruments as well. The main parts of a seismometer are the little sensor that measures ground vibrations, and then you need something to record the data. So these are examples of sites that are in the Canadian Arctic that we maintain and deploy. A couple different types of seismometers, either buried directly in the ground or protected in an insulated vault. You need to provide power for the site, so solar power for the most part. We actually don't use wind turbines because while they do help in the dark winter, the turbine itself puts vibrations into the ground, and that actually can often swamp the signal that we're looking for from earthquakes. They need maintenance up in the north all the time, so someone will be up visiting most years to go and maintain. Some instruments are on communication, so the data is in real time. Some record and you have to go collect it once a year. So there's a few examples of both where essentially it's a lot of batteries and a little computer in each of these boxes. In giving these sorts of talks in the north, you don't really have to talk to northerners about what the challenges are of working and living up in the north. It's enough to say that computers don't like -40 and neither do batteries. So there's lots of challenges with just the vast terrain, the extreme cold. Power has its challenges. Batteries don't like the cold. There's not much sun in the wintertime. And then wildlife. Bears and other animals, they see these stations from miles away and are intent on destroying them. And so they get ripped out of the ground, they get knocked over fairly regularly. So we do what we can to harden them, but it's very hard to make it strong enough for a polar bear to not be able to destroy it, or grizzly bear for that matter. The stations around here, this is the Yukon array. So we have Kluane Lake here, Haines Junction, which has a permanent network site on the top of Paint Mountain, and Burwash Landing has a permanent site, and there's a station at KLRS. And then there's the Yukon array stations that were put out in 2010. These are pictures of what they look like, and they're located on a number of these mountain tops, both on the Ruby Range, up Talbot Arm, and then in the direction towards the St. Elias Mountains. And these are providing valuable data on earthquakes, both along the Denali Fault, but also in this highly complicated region. Now, beyond seismometers, there's other tools we use, GPS and GNSS instrumentation. These allow us to measure millimeter scale ground motions over short and long time periods. When a big earthquake like this happens, the ground moves quite a bit. And it's not just that it shakes and goes back to where it was. There's permanent displacement or offset created by it. And we can use GNSS to study how much that was, how far in 3 dimensions, and that is a significant contribution to understanding how that earthquake actually ruptured. We have satellite imagery and radar. So this is something called INSAR. This looks at combinations of radar images taken from satellites. Unfortunately, this technique doesn't work up here. It needs no snow and no trees for it to work best. But in arid areas, this is a very powerful technique for looking at surface rupturing earthquakes. And then we have airborne reconnaissance. So this is helicopters, drones, optical imagery, LiDAR. This all builds up the picture that we use. And then we can say, I wonder how many people in the audience know this gentleman. He's got his, maybe not everybody knows him as a gentleman, but he's got his fingerprints all across a wide area of instrumenting Canada. Mike is a geodesist, and so he is instrumental through his career at installing and maintaining geodetic instruments that allow us to monitor millimeter movements of our crust across Western and Northern Canada. And so these are photos of him, relatively recent, I think, some of them. This is just from a month ago. Down the road at Million Dollar Falls. This was Mike going to collect data at the geodetic instrument there that recorded this earthquake. Okay, earthquake shaking in our communities. So this is where we come to local ground amplification, and I will go quickly here because I'm aware of the time. So the type of ground beneath your feet actually helps control how strongly you feel an earthquake. The soft sediments amplify earthquake shaking, and harder sediments like bedrock will transmit it with less amplification. So soft sediments will amplify both the strength of shaking that you feel, but it can also make it last longer. Whereas bedrock, it transmits through with lower amplitude and less amplification. You can think of it as if you have a bowl of jelly in one hand and a 2x4 in another, and you shake them, the 2x4 just stays as a 2x4. The jelly is gonna move back and forth. And at the top, if it's a big cube of jello, it'll actually move more than what you're shaking it below. So it's amplifying your shaking. This is an example from a magnitude 8 earthquake in Mexico. So we have the earthquake that occurred here in Mexico City was 400 kilometers away. Each of these is a seismogram that shows acceleration of the ground. They're all the same scale, where this number in each is the maximum acceleration observed at each location. So very close to the epicenter, there was strong shaking with 150 centimeters per second shaking. As we move away, we can see that this value decreases. Then we get to the big basin, sedimentary basin that Mexico City is built on. Just into that basin, we see that now actually we have more shaking than we did halfway to this location. And amazingly, in the middle of the Mexico City basin, 400 kilometers away from the earthquake, the peak acceleration, the peak strength of shaking was higher than it was right at the earthquake. And that is the impact of these local sediments that amplify the shaking. So that's why in our building codes and in our seismic hazard models, it's important to understand what the local site conditions are. And in Canada, this is how they're classified. Site classes A through E, where A represents hard rock and has the lowest amplification, all the way through E, which is soft clay and has the highest amplification. And we classify this using the average velocity in the upper 30 meters, something called VS30. And if you want to go study site classification and amplification, that's what you'd measure. So Haines Junction is a Class C, overall Class C, whereas Whitehorse is actually a Class D through much of the area. So how we do this, we put out seismometers. Geodetic instruments don't help for this part. That's what I think. Yeah, okay. If only I knew. So we put out arrays of these instruments and you just record for 1 to 2 hours the background noise. So that's cars driving, that's the wind noise. And then you can analyze that data and measure the velocity structure in the upper 30 meters. And by then taking that velocity, you can assign a site class. So what I'll show here is results from 2026 and 2024 work that was done actually in Haines Junction by University of Calgary, University of Victoria, and YGS. So a number of these arrays were set up throughout the area where this 1 to 2 hours of recording was carried out. And then the data was processed to look at what the various site classes are. Now on this map, these areas of red are the regions of permafrost from the YGS, I believe continuous permafrost. And the areas without the red are not permafrost. And what they notice is the color of these markers is the velocity, where the kind of blues and greens are site class C, and the oranges are working their way towards site class D, but they still are site class D. So the correlation that we see from this map is that the areas of permafrost are stiffer than the non-permafrost areas. So this is something important for us to consider going forwards. In a time where we have melting permafrost, we might be seeing throughout much of the north, the site class conditions change to ones that might amplify further. So currently, the permafrost makes the ground stiffer. It reduces the local earthquake shaking amplitudes, or I should say it doesn't reduce, it doesn't amplify it as much. Okay, the frozen ground may also help hold slopes together during the earthquakes. These are two example plots of the spectral acceleration. So this is a proxy to how strong the shaking is at a permafrost site in Haines Junction and a river basin site. And you can see that the peak amplification jumps from around 1.5 up to just over 2. So that's the impact that the permafrost is having in reducing the amount of amplification. So in the future, as permafrost thaws with the warming climate, the ground will become softer, and this could lead to increased earthquake amplification of shaking as we move forward. Okay, to wrap up some key messages and preparedness. So to summarize, December 6th earthquake was the largest we've had in Canada within Canada for some time. It confirmed the connector fault, this long hypothesized structure. There was over 200 landslides in the St. Elias Mountains. Could have been more if it wasn't as cold, if it wasn't during winter time, for instance, or if there was less permafrost. We study these sorts of events using a variety of tools, both seismic networks, GPS instrumentation, satellite imagery, and all of these networks in Canada are maintained quite collaboratively. It's both federal, territorial, and academic partners that maintain a lot of these networks that we use, and the data from these are all freely available. Local ground conditions matter, and these sorts of site amplification studies need to continue in most of Canada. It's only some of the major cities that actually have very detailed, what we call microzonation studies, where they look at this site amplification in great detail throughout a city. We need to continue to do better about getting this done in many communities across Canada. And finally, that permafrost, it currently might be reducing shaking hazards, but as it continues to melt, this is something that we're going to have to deal with very carefully and properly with northern communities, especially areas of rapid permafrost loss. Sorry. So what can we do? Be aware, the Yukon is earthquake country. Large earthquakes have happened and they will continue to happen. Be prepared. It's a good idea to have a plan, an earthquake kit, and practice your drop cover hold on, with the most important part of that being the hold on. We see in a lot of drills, the drop cover is great, but when you don't have the shaking, moving your table or chair away from you, you can forget about the hold on part of it. In a big earthquake, your cover that you're under may try to walk away. And, you know, a little plug for the scientists. The Did You Feel It reports are very helpful for us in continuing to build this picture of local amplification. While not as clear as an actual deployment for site amplification, looking at these reports coming in over communities allows us to get a better idea of what the shaking levels are and overall site amplification might be for one community versus another, which still does contribute to our improving our seismic hazard and our resilience towards these sorts of natural disasters. And with that, I will I'll acknowledge that this sequence occurred on the traditional territories of the First Nations, including the Kluane First Nation and White River First Nation. The site response work shown here was conducted on the Champagne and Ajac First Nations, Kwanlin Dun First Nation, and the Tanquachan Council. It's a collaborative effort between YGS, NRCan, and University of Calgary, a lot of this. And thank you to the Yukon University and Yukon Science Institute for organizing this. And many thanks to Haines Junction and all the volunteers that helped put this together along with KLRS. Thank you.
I'm sure there's at least one question in the House. We'll get to that in a second. I do want to point something out.
What did I get wrong, Mike?
No, you. What's interesting, in my working career, GPS was just being born.
Mm-hmm.
And since then, the combination of traditional seismology goes back hundreds of years in some cases. And GPS, it's old and new technology. But also with that comes a lot of local knowledge. And thus the felt reports are important. On the West Coast, we used a lot of First Nation Indigenous knowledge to put the picture of the last great earthquake, that's magnitude 9, put that story together. So all these things work in tandem and are all important. So the felt reports, I'll post the link on Facebook in a day or two. Please think of it next time you feel an earthquake. Don't feel like it's trivial. It's really, really useful.
And I'll also say to that, it's useful to still post that you didn't feel it, even if you know people that did. So the null report is still also useful to us because it often will have that will have an impact on the very local site conditions. Maybe one house is built on a bedrock promontory just below the surface or something like this. So this still helps with local site conditions.
Just to finish up on that, the combination of the GPS and the seismology has made huge, huge inroads. And I know there's at least one person in this room who was up Mount Logan with us a few years ago with GPS, one of the first surveys in this part of the world in 1992. And that's what started. I was able to continue that research after Logan. But that GPS, the satellites, what we now have is just absolutely amazing. Like you think of it, satellites and millimeter accuracy. It's pretty amazing. Anyway, we are going to, of course, want to have hear from you. Some questions. Please keep the questions brief, and please wait for me to come with a microphone. So, where would you like to start?
Or I've scared everybody.
I've never seen so many quiet people in here. Questions? We have 70 or so experts in here now.
What was that?
You did such a good job, but don't let that go to your head, okay? There we go. There must be some questions.
What about predicting the next one?
Yes. So the P word is one that we don't use very often in seismology. And the best analogy I can give is in some portions of the world, we're getting close to where we might be able to issue a forecast. So actually in Japan now, after the recent large earthquake earlier in the year, they actually they posted a forecast that there was an elevated probability for another earthquake to happen. Part of the reason that they can do that in Japan is they have a very, very long record of these significant earthquakes that have happened for hundreds and hundreds and hundreds of years. And so the challenge with a fault and when is it going to rupture is it comes down to how much stress does that fault have on it. When you rupture an earthquake, you relieve some of the stress. However, not every earthquake releases all of the stress, so it doesn't always go back to zero. So in order to build up a really good picture of how much stress is on that fault and how close it might be to rupturing again, you need a really long history of all of the significant earthquakes that occurred on it. And there's very few places in the world where we have that. So what we do instead right now is we give probabilities of how likely significant ground shaking is going to occur in an area, but we're not able to predict a date time. We can give a time range of when it's likely that something could happen, but not. If you ever see, on March 12th at 12 p.m., there'll be a magnitude 5. Nowhere in the world can we do that. Yeah. All we can say is that there's, so in Japan, they say there's an elevated probability of a magnitude 6 for the next 3 weeks. But that is simply because of the really long record that they have.
What about a small earthquake, 3.5? That's releasing a little bit of pressure.
Yeah.
Would not help with the prediction?
No. Well, so it helps us define where the faults are. But the amount of energy that a 3.5 releases, because earthquake magnitudes and energy release is a logarithmic scale, a magnitude 3 releases some energy, a 4 releases 30 times that, a 5 30 times that. So the amount of energy released by a 3 is essentially a drop in the bucket compared to a 7 or an 8. So what's really important about capturing both the large and small seismicity is that small seismicity allows us to see where those faults are, because the big ones don't happen that often. And so those small ones show us where they are. So the aftershock sequence, all those green dots, those are highlighting exactly where the fault is, which we can't see easily just from the one main shock alone. So we do actually need to combine both of these together. but they don't help with prediction specifically. It's a good question, and it's one that comes up a lot. And one of the questions we get is, well, you can predict the weather, why not earthquakes? And it just comes down to timescale. You get a storm many times a year. You have measurements of temperature and pressure all over the place all the time. So there's a lot of data that goes into those models. The time scale that we work with for earthquakes, if we want to be able to accurately predict when the next 7 would be, we would need to have hundreds and thousands of data points of 7s going back in time to be able to accurately predict when the next one would be. And because 7s don't happen here very often on the same fault, we don't have that history of measurements to be able to accurately predict forwards in time. It's a time scale thing.
Can cats and chickens predict earthquakes?
I've heard so, I'm not that type of scientist, so I don't know. If it helps, then you can use that as a warning.
Did you want to touch slip,
Oh, how much slip?
ETS?
Oh, yeah. We can. Okay, so in some faults, particularly subduction zone faults, there's another phenomena that's going on, and that is something called episodic tremor and slip. So this is something where seismology and geodesy came together very nicely to tell a very interesting story. So subduction zones, you have the big magnitude 9 earthquakes, but they actually also exhibit some very, very small earthquakes, and they're tremors. And so what happens in different subduction zones is you have a period of time that repeats. It's episodic, where a small part of the fault will actually slip a little bit. So it releases hundreds and thousands of tiny little earthquakes. They don't really reduce the overall period of time for a magnitude 9 megathrust earthquake. But you can see in the geodetic instruments, so then the GPS data and the seismic data, you see a period of time where there's a whole bunch of little earthquakes that happen. And then you see, so in the case of the Cascadia subduction zone, so BC, Washington, Oregon, you have, let me orient the right way, you have the Pacific plate subducting beneath the continent, and they're stuck together. But during this period of episodic tremor and slip, this is actually a period of time where the North American plate slightly slips back up. It releases a little bit. You can see that oceanward motion in the continent. So every 14 months, Vancouver Island slips a little bit back towards the Pacific. And then it stops and it continues to be squished back against the continent again. And in Cascadia, that's about a 14-month periodicity. In Japan, it's about 9 months. It varies depending on the age of the incoming plates and some other factors. But this isn't something that we see on very many continental strike slip faults. This seems to be mostly a feature of subduction zones.
So just in case there's any questions, what we can do with the GPS, they operate 24/7, and we're constantly every second or every 30 seconds calculating a position. And then we look for a change in that position over time. And so when we're talking about the slip, what we were actually able to do was detect the long-term trend, it's stopping and then slipping backwards. And then 2-3 weeks later, it started up again and then slipped backwards.
Yeah.
It was, when that was discovered, it was pretty exciting.
Yeah.
Because it had not been seen before, and that was Herb's work.
That was, yeah.
Well, any other questions? Sorry, what's your name?
Is that why they say that Vancouver is overdue?
Not necessarily due to ETS. So being overdue is a little bit of a misnomer. It's actually just starting to come into the window where it is reasonable to happen. So Cascadia subduction zone, it has an average recurrence interval of about 500 years, but the range seen is about 300 to 900 years. And we're just now getting to that 300 mark. So from my perspective as a seismologist, I wouldn't say that we're overdue. We're just in that period of time where, Victoria, we also, part of this probabilistic way of describing things and not predicting is we wouldn't say the recurrence interval of a particular size earthquake. What we would say for Victoria and Vancouver is there's a 30% chance of damaging shaking to occur in the next 50 years. For Victoria, it's about 20% for Vancouver, just because it's a little bit further inland and there's not quite as many crustal faults in the overriding plate near Vancouver that we know as there are on Vancouver Island. And so, there's similar statistics for up in the north. Whitehorse is quite a bit lower than Vancouver, and Haines Junction is lower than Vancouver as well. And but it's kind of in the 5 to 10% per 50-year range.
Just to follow up on that, the thing about gets blown out of proportion in the media, overdue for an earthquake, we get sucked into the media asking us, when is the next big one? Well, that's a real question. It's like every 200 to 600 years is a big one. But as we say so often, there are a lot of crustal earthquakes, and they can be as damaging locally.
So that's what I mean
A
when
really good example of that is Christchurch.
Yes,
right?
in New Zealand, yeah.
So, good point.
If you take this magnitude 7 and put it beneath Vancouver Island, that would have been huge amount of damage. If we'd moved it to a populated center and had it be shallow in the crust, then it would have caused significant damage. And so that's what this 20 or 30% in 50 years damaging shaking, it counts for the various types of earthquakes that could cause damaging shaking.
Okay, I'm curious about the role of other natural things happening right around the time of an earthquake. For example, the one in December, there was also a volcano active in Hawaii, and there was a huge solar flare, and they were all right around the same time. So, what's the role of all this when we're looking at our earthquakes?
Yeah, so on a local scale, if there had been a volcano nearby, there can be earthquakes associated with volcanoes. In fact, magma moving within the crust will cause small earthquakes to happen. But Hawaii is erupting or almost erupting almost all the time. So that system is a completely different tectonic system that's unrelated to the earthquakes here. So Hawaii is what we call a hotspot volcano. And so that's a column of hot rocks, and it's not it's molten rocks coming from deep within the earth, and they're penetrating through the middle of the Pacific Plate. And the Pacific Plate is just, as far as it's concerned, happily moving over top of that. So Hawaii itself wouldn't be related to earthquakes that are happening here, for instance. Solar flares as well, and that sort of activity, it can cause a lot of interference on our instrumentation. But it doesn't have penetration into the crust in order to, as far as we know right now from science today, that sort of thing isn't impacting these sorts of significant earthquakes. Smaller earthquakes can be impacted by, for instance, by the amount of precipitation. There's water in the crust everywhere, so if you bring in a lot of water, you can have a higher propensity for landslides. They could be easier to trigger landslides by earthquakes in areas or in periods of time where you have a lot of rain. But otherwise, the amounts of energy that we're talking about are stresses that have to be overcome to have a significant earthquake. Most of these aren't able to produce enough energy to overcome that frictional stress that's needed for a large earthquake.
So what about fracking that occurs?
Yep.
Yeah.
Yeah.
We hear about
So
it.
we hear about it, and so hydraulic fracturing, so there's a couple different things. There's hydraulic fracturing where they inject high pressure fluids into a formation to open it up and allow oil or whatever to come out. There's also wastewater injection, which different purpose, but same thing, you're injecting fluids at high pressure. So what happens is when you put those fluids in, the whole idea is you're opening up the cracks in the pore space to allow whatever material you want in there to be able to flow out. So in areas where you have pre-existing tectonic stress, so for example, in Western Alberta, we have the huge Rocky Mountains, just a little bit over to the west. And that was a major mountain building episode. It had massive amounts of stress built up to build these mountains. And while there still are some tectonic earthquakes in the area, that mountain building has mostly come to an end. But there's still lingering stress in a lot of those rocks and the nearby areas. And with the Western Canada Sedimentary Basin, which is the home to all of the oil there, it covers all of those bedrock faults. So we don't know where all of them are. So when you inject fluids into the ground and what you essentially do is increase the fluid pressure in the ground, that opens up cracks. If there is a fault in the area that those fluids can get to, that high pressure fluid can reduce the stress, the force closing that fault together a little bit, and sometimes that's enough for it to overcome the friction holding it closed, and it'll slip in an earthquake. So when you pump fluids in, you can produce earthquakes, yeah, if you're in an area that already has faults that are stressed a certain amount in them. Yeah. And we see those, in Western Alberta, Northeast BC. They're regular. They're not the most regular earthquakes that we have, but they happen quite a bit.
I just have, you mentioned there's a lack of instrumentation.
Sorry?
You mentioned there's a lack of instrumentation in the area. So how are you certain where the green dots go?
Yeah,
And what
good
would
question.
the accuracy be?
That's a very good question. So the most difficult thing to constrain, unless you essentially have stations, seismometers right on top of the earthquake, is the depth. So like these earthquakes, they were recorded by tens, 20, 30 instruments spread across Canada and Alaska. So the horizontal position of these earthquakes, for all of those green dots that I showed on the map, those are going to be probably within 5 kilometers of where the earthquake actually happened. And then the green dots that I showed you are not actually the original locations. We've then gone and applied another technique to the original locations that improves their accuracy relative to the other earthquakes in the sequence. So we can become very confident in that overall pattern. What is difficult without dense instrumentation is the depths of the earthquakes. We know that these are relatively shallow. Most of these are shallower than 20 kilometers depth. We wouldn't expect earthquakes in the St. Elias to actually be deeper than 20 kilometers for the most part. And that's because the crust is so thick there and it's being built, it's actually very hot. So when you go deep into the St. Elias Mountains, as you go deeper within the earth, the temperature increases. This is called the geothermal gradient. It's part of what geothermal energy relies on. If you have a high geothermal gradient, you don't have to drill as far to get warm. In the St. Elias Mountains, we know that by 20 kilometers depth, the crust is hot enough that you actually can't start earthquakes there. The crust can deform more like plasticine. It doesn't break or snap like a brittle rock. But yeah, so horizontal positions, those are pretty good to 5 kilometers. I mean, as a scientist, I would love for there to be an instrument absolutely everywhere, but not everybody wants to look at one of those. And, there's a density to cover to get kind of the fundamental information. So in this area, I didn't talk about it on one of those figures, but the plot that showed the earthquakes as a function of time, on that first plot, there was some black dots along the bottom of the earthquakes. That represents what we would call our magnitude of completeness. So that is the smallest magnitude at which we're confident we've got every earthquake. So it's only that and larger. So for the St. Elias Mountains, the magnitude of completeness is about 2.1. So that's doing relatively well for a remote area globally. It's lower, sorry, the magnitude of completeness is higher, so a little bit worse in many other parts of the north where there's fewer instrumentation. This Yukon array network actually densifies the coverage down here quite a bit.
Any last questions? So this gentleman spoke in Whitehorse last night. We have more people here tonight than he had in Whitehorse last night. Yay.
Well done.
Okay, we're going to segue into this.
So this is just a demo of a very simple seismometer. If you want to come up later and take a look, it's safely under that desk just so that it doesn't get stomped. But what it is it's called a Raspberry Shake. So if you're familiar with a Raspberry Pi single board computer, it's a seismometer running on a little Raspberry Pi board. And these are produced, this started as a Kickstarter campaign a number of years ago as a hobbyist instrument. And I think now today there's about 2,500 of these around the world. And so out of the University of Victoria and the GSC, we run a outreach program called School Shake, where we put these in schools in the Victoria and part of Vancouver Island area. So I brought one with me. One of the things that we love to do in the kids love to do in the classroom is make their own earthquakes. We have one of these in our office. Mike might remember. It's just down from my office. And if I don't know that there's a school tour in the building, I sometimes get terrified because suddenly there's a huge thump and the whole floor shakes. And so what this will do is it will pick up all of the vibrations that are going on in through the floor. So I saw somebody tap their foot. That's that spike in the middle right now. Well done. But it's a fun tool for seeing how earthquakes work. So do we have a volunteer in the front row that wants to stand up and just jump once? There we go. Okay, so there's a short delay in this, but you'll see there's that jump that got picked up there. Now, do we have a volunteer in the back row that can do about the same thing? Whoa, very good. Okay, so what we'll see is we'll see a similar spike. In this case, it was bigger because you jumped harder. But if we were to jump the same, what you'd see is the one that happened at the back of the room had a lower amplitude. And that's because it was just that much further away. The signal got attenuated as it traveled through the floor to here. You can also see things like, well, when we were setting up, I was pacing around, and you can see all the footsteps of people walking around. So this sort of instrument, which is just a little thing sitting on the floor like this, I can pull it out in a minute. It's this big, and like if you put that on a concrete floor somewhere, this will pick up earthquakes from around the world. So not small ones, like magnitude 6s and 7s. These would pick up earthquakes of that size from around the world if they were in a quiet place, away from furnaces and that sort of thing.
I see a frown here when you mention from around the world. Let's remember that the earthquakes or the energy from earthquakes does travel around the globe. The bigger the earthquake, the further it travels and the longer it travels time-wise.
Yeah.
And
And
it's a whole other area.
It's a whole other field of research, but like from that magnitude 7 earthquake, the signals from that earthquake, they traveled around the world multiple times. So on very precise, like well-insulated, quiet, high-precision instrumentation, we call these they're called R1, R2, R3, L1, L2, L3. The number refers to how many times you've seen it go past. As it goes. So like for a magnitude 9 earthquake, we can get into normal modes. The earth actually expands and compresses when a big earthquake happens in a bunch of different ways. And one of the ones that's easiest to talk about is what they call the football mode, or in Europe, they call it the rugby mode. And that's essentially with a big earthquake like that, the earth squishes and expands like this, and it can ring like that for days. We don't feel it. But very precise instrumentation, seismometers, geodetic instruments can pick up that sort of ringing of the earth. So a significant earthquake on the other side of the world doesn't affect us, but our instrumentation in Canada or other places is used by others around the world to study these earthquakes, or the earthquakes, but also the structure. So for example, our instruments that we have running in Canada, we use those mostly to study where the earthquakes in Canada are. But if we want to look at what the deep structure of Canada is, by deep I mean 200 kilometers or so, we actually predominantly have to use earthquakes recorded in Canada, but happen somewhere else in the world, because we need them to come up below our stations And that allows us to image the structure of the Earth deep beneath the station. But to have it come up almost vertically beneath our station, it has to occur somewhere many, many thousands and thousands of kilometers away.
Questions, last questions. Going once, going twice. No?
How about a big jump?
We could do that too. I want to thank you, Andrew, for a great talk. It's been excellent having you here. From a personal perspective, seeing how the seismology and geodesy, how we're finally getting that to work together, it's a huge thing. Well done, and thank you so much for coming up, and thank you everyone for being here this evening. Thank you.
Yep. Thank you for coming, everybody.